This video is going to be a review of how complex fractions are simplified. I'm assuming that you came from the limits video on complex fractions. There was a link in it to take you to this video in case you're a little bit rusty. If you found this video by accident, looking for how to simplify complex fractions, this will still work and it might help you for the, oh, I had forgotten how that worked question. But we're going to go through this, and then in the description section down below, there are links, one to take you back to the limit, and I think at a later date I'm going to put some practice problems down in there for this, but you'll practice this technique enough on the limit section to verify that you understand all the nuances. So let's get started. When I teach complex fractions, the limit section on complex fractions, I have probably the majority of the students in my class tackle the concept of simplifying complex fractions with, let's call it method one, and then a smaller percentage tackle them with what let's call method two. Now, method one is the way that you would take, let's say we have this example right here of 2/3 minus 1/4 over 5/6 plus 1/2. We're just going to start with basic algebra, because if you can remember how you do it with numbers, it works the exact same way with variables. It just looks kind of a little more bizarre, but the same techniques of looking for the common denominators and what you do with them, same thing. Okay, so let's go back and retrieve what happens with simple fractions. Like I said, it's kind of a misnomer since these are complex fractions, but simple as in no variables. All right. Some students use method one, and what they do is they combine the two fractions in the numerator together to make one fraction, and then they combine the two fractions in the denominator to make one fraction, and then they divide both fractions and come up with an answer. Now, that works just fine with the stuff that you learned in algebra in high school and junior high and college algebra. And sometimes it works just fine in calculus, but when I see errors with this technique on tests, it's almost always with students who use this method one, because it gets very involved and very convoluted very quickly. And so even though it's a legitimate method and there's nothing wrong with it, it wouldn't necessarily be the simplest way to tackle these problems. But I'm going to remind you how it worked, and then right next to it, I'm going to work the same problem, the method two way, to show you how much cleaner it is on method two. I could almost guarantee you that if the person who taught you complex fractions had also taught calculus, they would be teaching you method two and not method one. All right, so let's look at method one. Like I said, it's legitimate, but for calculus, sometimes if you can streamline it, it makes it just a little easier. So let's try this method one, and let's find a common denominator for 2/3 and 1/4, and that would be 12, wouldn't it? So you would try to get a common denominator of 12. So you would multiply this fraction by 3/3, so you'd have 12ths. You'd multiply this one by 4 and multiply the top by that to be legal. Now on the bottom, you could also make it be 12ths, but let's just make it 6 because that's what it looks like. And you'd multiply this one by 3 and 3 here, and 6 is already there. And so what you would have, and I actually did 2 steps at one time, is you would have a 12th minus 3/12 over 5/6 plus 3/6. And then you could say, well, 8/12 minus 3/12 is 5/12. 5/6 plus 3/6 is 8/6. And you could reduce the 8/6, but you don't have to because we're getting ready to divide it out. And so we would say this is 5/12 divided by 8/6. And remember that to divide by a fraction, you multiply by its reciprocal. So 6 goes into 12 twice. and you would have 5 over 16. Legitimate. I mean, there is nothing wrong with this. Works smoothly. Not a problem. Okay, now let's look at an alternative form. And you have 2/3 minus 1/4 over 5/6 plus 1/2. Same problem. And this time, instead of looking at it as two pieces where you have a top set and a bottom set of fractions, what I want you to do is think of it as four fractions inside of a fraction. So you have 2/3, that's one, 1/4 is the second, 5/6 is the third, and 1/2 is the fourth fraction. And you look at it and go, what is the least common denominator of all four pieces? So 3, 4, 6, and 2 would all go into 12. So same 12s. We're going to multiply top and bottom of this fraction by 12. So you'd multiply the top by 12 and the bottom by 12. Now, the 12 is actually going to get multiplied in a distributive fashion across the two fractions. And the error that I see here, which usually gets taken care of pretty easily, is that when they multiply 12 times 4, they will go, oh, 4 goes into 12 3 times. And then they would try to multiply this 3 times that one instead of by the entire 12. So in order to keep things straight, and since we know that this 12 is going to multiply both fractions in the numerator, it probably will decrease your chance for error if you just go, okay, I'm going to write the 12 down next to each fraction so I can do that little cancel slash to my little heart's content. So instead of doing the distributive property in my head, I'm going to write it down. So then you would say, well, this 3 goes into 12 4 times, and that would leave me 8. And this 4 goes into 12 3 times, and 3 times 1 is 3. And that's a minus, not a plus. And then this 6 goes into 12 twice, and 2 times 5 is 10. Let's go for black. 10 plus, and this 2 goes into 12 6 times, and 1 times 6 is 6. So 8 minus 3 is 5, and 10 plus 6 is 16. So you can see right there, if you compare steps, you get to that final answer a little bit faster. And again, every once in a while you'll hear me say it's better to be slow and right than fast and wrong. Okay, so sometimes speed is not your best choice if you're not comfortable with the new technique and you're comfortable with the old technique and it takes you a little longer. There's nothing wrong with that. But you have to be really careful with this process to not lose anything. So let's try one with some variables. And we would have 1 minus 1 over x squared, 1 minus 1 over x. And if you want to do that method 1, that's fine. Okay, I'm going to do method 2, and we'll just check and make sure we have the same answers. So you look at these fractions within the fraction, and even though 1 is not seen as a fraction, I mean, it looks like an integer, but you can make an integer be a fraction by mentally putting it over 1. So 2 is 2 over 1, 5 is 5 over 1, 1 is 1 over 1. So there's 4 terms or items inside this fraction. They don't all have to be complex fractions, but you look at the fractions within the fraction and say the least common denominator between an x and an x squared is x squared. So you're going to multiply top and bottom by x squared. So this gets multiplied by x squared. Everything on top gets multiplied by x squared, even if it wasn't a fraction to start with, because what you multiply the top by, you multiply the bottom by, and you multiply all the top, not some of the top. Now, so here we go. So this x squared times 1 is x squared. This x squared cancels this x squared. and you have minus 1 over. X squared times 1 is x squared. This x cancels out one of these x's, leaving you minus x. Now, I'm going to ask you a question. I'm going to tell you the answer up front. The answer is no. Okay, so the answer is no. Now, does this x squared right here cancel this x squared right there? And the answer is no. So hopefully you said no. Let me explain to you why it doesn't. Because it's so tempting to say, oh, there's an x squared over an x squared, and we're canceling x squareds over here. Okay, so why can't we do that? Well, these are multiplying, so they are factors of each other. Okay, you can reduce out because some teachers will absolutely get ill if you say cancel in front of them. So be careful who you say that in front of. They'll, I've actually seen people all but throw up when I have heard students say that. So keep that in mind. But if you had something like 4x squared over 3x squared, sure, these would cancel because they're just multiplying the 4 and multiplying the 3, and they are not tied to another entity. But if they're tied to the other one, then these two are multiplying each other, but they're not a factor of this term, so you can't cancel them. Okay? Now, the mathematically sound thing to say is you can't cancel things that are not factors because the act of canceling is to divide it out. And that's why math people get ill when you say cancel, because cancel doesn't tell you the math technique you're using, because when you first learned how to take 4/8 and to reduce it, and you now say there's a 4 in common, the way you first learned it is to divide the top by 4 and to divide the bottom by 4, and these are the ones that cancel. 8 divided by 4 is 2. This did not cancel into this one, okay? You divided the top by 4, and these canceled, leaving you 1. I shouldn't say canceled. Those divided out and left you 1, and these divided out and left you 2. And we just developed a shorthand, all of us do, over a period of years, saying, oh, and this 4 goes into this 8 twice. Okay? But that's not actually what it was when you first learned it. So at any rate, those x squareds do not cancel each other. And I had a class one time that had the dickens of a time trying to keep that in mind. So I told them this story, and I'm not going to tell you the whole story. But what had happened was it was actually my husband and I had our daughter swinging between us in the mall trying to keep her kind of self-contained when she was like 2. Okay, so we're swinging her in our hands. And so think of her as this little, see the little hands right here? And she's holding on to mom and dad. Okay. So my class couldn't keep up with the idea about factors, but they understood that if you have a horizontal line like this, and it could be a plus with a horizontal line or a minus, if you think of this as being like a little tiny person and they're holding on here and they're holding on there, you cannot chop off parts of what they're holding on to. Okay. So sometimes I'll see students and I'll say, do these cancel? And somebody in the room is going to look up at me and go, no, little hands. I go, yeah, that's true. So if it helps you to keep up with it and not do it incorrectly, I'm all for a story that goes along. Right. So I can't cancel these out, but they look awfully suspiciously like they might be related. So anytime you see things with powers and maybe some variables in common, you should try to see if you can reduce it, factor it and reduce it. So the top is the difference of two squares. So it'd be x plus 1, x minus 1. And on the bottom, you have x times x minus 1. And if you've forgotten how to factor, there's a review on how to factor that's associated with the second limit video. So go and find it. Now, this x minus 1 cancels this one, and you're left with x plus 1 over x. Okay? All right, and here's the question. Do these two x's cancel? And the answer is no. Okay, little hands. All right, because this x is being held on to that 1. All right, here we go. Another one. Okay, x minus 4 plus 9 over 2x plus 3 over x plus 3 minus 5 over 2x plus 3. Now we've got 3 terms in the top, 3 terms in the bottom. Doesn't have to be just a binomial, but I've got at least one complex fraction set up, right, with a fraction inside of a fraction. So we use the same exact technique, and these are all understood to be over 1, correct? But the other two are over 2x plus 3. So the least common denominator is 2x plus 3. And what you're going to do is to multiply top and bottom by 2x plus 3. And since I do like to do the little crossing out, when I can to cancel, I'm going to write this down next to each term. Now, technically, you're multiplying 2x plus 3 times x and 2x plus 3 times this negative 4. And I don't know if that makes you feel better or worse than to say, I'm kind of comfortable multiplying binomials using the the FOIL method. So I'm going to multiply it using the distributive property like this, where you do the FOIL method. And if you don't like that, go back to the other way where you write 2x plus 3 down to next to each one. And you're going to multiply this by 2x plus 3. So these are going to get multiplied using the FOIL method. Or you can do them separately. Okay? So when you do this, 2x plus 3 times x minus 4 turns out to be 2x squared plus 3x minus 8x minus 12. Okay. And then this 2x plus 3 cancels this one, and you have plus 9 over 2x plus 3 times x plus 3 is 2x squared plus 3x plus 6x plus 9 minus 5. Okay, because this 2x plus 3 cancels that one and leaves you 5. Now I can clean this up just a little bit more. So it's 2x squared minus 5x minus 3 by combining like terms. And one of the things you get used to in calculus is if it looks like it might factor, you better try. So these are trinomials that don't have a lead coefficient of a 1. So you can either do the trial and error method, you can do what some students call the box method, the A times C method. I grew up with the trial and error method, which by the way means try it and you're wrong, but you get faster at it as you get used to it. So you go, all right, what can multiply to 2x squared? Well, one of them has to be 2x and the other one has to be x because 2 is 2 times 1. And thank goodness what multiplies to 3 is just 3 and 1. So all you have to do is try to figure out how to get 5. So 3 times 2 would be 6. This is the 1. I need a negative 5, so this would be negative, this would be plus. That's sort of how the trial and error method works. And this also is 2x squared, so you'd have 2x and x. And the things that multiply to 4 are 1 and 4, and 2 and 2. But you need a 9 out of it, so 4 would be the more extreme. That would give you 8x right here. And then extra 1 would give you 9. And I want them all to be positive. So this 2x plus 1 and this 2x plus 1 cancel out or reduce. Because that's like sending the whole family home, like here's a parent, here's little hands. Okay, I know you're going to get tired of that analogy, but students tell me they can hear this on the test. They hear me on the test going, no, don't do it. Little hands. All right. And whatever I can do to help you save a point or two on the test, I am willing to be made fun of if it helps you save a point here and there. So this reduces down to this. And that's your answer. Now, one more problem, because sometimes teachers like to bring things up from your past and see if you still remember how it works. Now, right at the moment, this doesn't look like a complex fraction problem. Okay, I'm not sure what it actually looks like, but it doesn't look like it's complex because I don't see any fractions in a fraction. But if you look at those -1 powers, the -1 power says you should take whatever it refers to and move it to the other side of the fraction bar. So if it's on the top, it goes to the bottom. If it's on the bottom, it goes to the top. Sometimes students will hear me say it's not happy, it wants to go to the other side of the fraction bar. But it only applies to the part that the exponent applies to. So this -1 applies to just the y. If they wanted it to apply to x, they would put it in parentheses. This -1 right here applies to x and y because it has parentheses, and this -2 applies just to this x right here. So let's write this without negative exponents, and you'd have x over y minus 1 over xy over 1 over x squared minus 1. Now it looks like a complex fraction. And you look at it and you want to come up with the least common denominator. So you need the biggest powered term combination. So the biggest y term multiplier is y. The biggest x is x squared. So my least common denominator is x squared y. And I'm going to multiply top and bottom by x squared y. And so that I can reduce without having to worry about missing something along the way, I'm going to write this down to next to each one. By the way, while I'm sitting here, if you keep going across like this to simplify this out and you wonder why I don't, you can go over one time and then you have to go down. That's good form. If you keep going on over and over and over like this, that's actually considered bad form. It's like comparable to a run-on sentence in English. So you should only have one equals per line. Sometimes they do that in books to save, in the old days, save paper on an actual hard copy book. But you're not supposed to go sideways and have more than one equals per line. So here we go. Now this y cancels this y. Okay? And x times x squared is x cubed minus. This x takes out one of these x's, and this y takes out that y. So you have minus x. Okay? This x squared takes out this x squared, and you have y minus. Nothing cancels there, and you have x squared y. As you can tell, I'm not one of those teachers that gets nauseous if you say cancel. I don't know if it's because I was trained as an engineer and not as a mathematician, which I love to teach math and have done for 30 years. But anyway, I don't mind the word cancel. Now, you look at this and go, you know, there's some x's in common in the numerator. There's a y in common in the denominator. I better take another look at this. So let's see. X could factor out of the top, and that would be x squared minus 1. And y could factor out of the bottom, and that would be 1 minus x squared. So see how the x squared minus 1 and the 1 minus x squared are so close. It's almost like they've been in a revolving door and you just kind of really want them to go like this. Okay, so you can do that not by multiplying by a negative, but by factoring out a negative. So you remember to factor out is to divide out. So if you're going to take a -1, let's go over here. I'm not going to multiply by a negative. I'm going to divide one out. So you would have a +1 divided by a negative is a -1. See how a negative times a negative gets you back that 1? And a negative x squared dividing out a negative is plus x squared. You can always check yourself. Does this negative times -1 get you 1? Yes. Does this negative times plus x squared get you negative x squared? Yes. Okay, so this is actually a negative. I'm going to pull it in front. And this might be better written as x squared minus 1. See the little square right there? Okay, x squared minus 1. And lo and behold, this cancels this. And you're left with the negative x over y. Okay, so I hope that helps you to remember how to simplify complex fractions. There should be a link in the description below that takes you back to the limit video. And I wish you the best of luck on simplifying complex fractions.